Waterfowl hunting is a common activity across the country. It typically entails a hunter heading into a marsh or swamp using a boat or waders to attempt to trick ducks and geese into coming in a shooting range to be harvested. The Waterfowl Retrieving System Group has been tasked with creating a dog replacement to eliminate the risk posed to dogs when hunting in close proximity to alligators and snakes. The robot in question, the Fowl Fetcher, must be an innovative design and will be capable of traversing multiple terrains in the case that a bird is downed on land or in water. It will also have some autonomous systems, such as an automatic return function, and the ability to mark a bird on the controller screen using the integrated camera technology communicated from the robot back to the controller.
After researching different drive systems as well as grabbing mechanisms, a decision matrix was set up to get the best combination. It was found that a screw pontoon robot with an arm mechanism that can be raised and lowered would be the best option given our matrix. Calculations were run to find the ideal size of the pontoons to maximize buoyancy and minimize weight. It was found that this size would be an 8-inch diameter PVC pontoon, which would allow for up to 50 pounds while still floating the center of the pontoons out of the water. The arm mechanism was chosen to limit the number of motors needed as well as to give the most effective style of grabber that should be able to perform most successfully. A cable system was used to actuate the arm so that the motor would be able to be frame mounted instead of arm mounted to limit the amount of weight that needs to be moved when raising the mechanism. The cups on the arm for grabbing the duck were designed to be easily interchangeable to allow testing of different geometries. The operator of the fowl fetcher will use a dual joystick controller to navigate the robot out to the downed duck, utilizing the robot's live camera feed displayed on the controller. Once they have the duck in sight within the feed, they are able to place a target on the duck on the controller's display. This target input will be utilized by the program to autonomously retrieve the duck using a depth camera and the robot's arm maneuvers. After the duck is secured within the robot, the operator will press a button on the controller signaling for the return. This return will be implemented using a waypoint-based GPS navigation algorithm, which will be autonomously retracing the steps that it previously stored in the GPS with the breadcrumbs it left on the path out to the duck.
This senior design project has proven to be a difficult task due to its innovation that is required as well as the lack of resources to compare to. The given product proves its functionality and sets up a future for this platform to continue to grow into a commercially produced product. All systems are prepared to be implemented in a real-world environment. The drive system has been proven effective in water and on land as it has been operated in both cases. The arm assembly can be effectively operated remotely to pick up objects and place them into the robot. GPS tracking has been proven to work as points are dropped along the robot's route, and a compass has been implemented to guide the robot back to the user as it returns on the tracked path. There is also a vision system that is capable of tracking an object, and in this case, a duck decoy was tracked. This will allow the user to track the downed bird as they retrieve it. Overall, the effectiveness of this innovative new robotic design has been demonstrated and is ready for Phase 2.
In the future, it is recommended that the robot be downsized if possible to limit the overall weight. Scaling down the size of the robot would also allow for smaller components and a decreased price, allowing for the possibility of manufacturing and selling them as a commercial product. Upgrades to the drive system that allow for easier turning on hard surfaces with higher drag would be recommended as well to allow for a more effective land-based retrieval system. Implementation of the GPS return system through motor controls and adding the depth camera and image recognition to the system would allow for the completion of the autonomous portion of the project. With regards to the vision system, a large multi-class convolutional neural network is currently being applied and is too large for implementation on the robot. However, someone with knowledge in machine learning should be able to apply transfer learning to our problem and reduce computation costs enough that it could be implemented on the robot. The electronics box is currently sealed to ensure waterproof capabilities. This could lead to heat issues in the future, with longer run times and higher power outputs. It is recommended that this is addressed in the future through heat sinks or internal fans to ensure all components are safe and do not become overheated during operation.